What is going on, everybody? It is Mr. Gustin, and I'm back in the physics classroom. Today, we are discussing power. As of right now, we started off this unit discussing work or changes in energy. We moved into different types of energy, kind of adding our kinetic energies, our spring energies, our gravitational potential energies, and then we started talking about conservation of energy, where if I have the right system, I can have my energy conserved instead of having work be done on it. Well, today, we're going to look at both work and transformations or changes in energy in terms of their rate. How quickly is work done, or how quickly is energy changed or transformed? And we have a secret name or a special physics name for the rate at which energy is transformed or changed. And that name is power, okay? And we oftentimes in this class don't discuss mechanical power. It's usually discussed in terms of electricity, but mechanical power is still a thing, and it's oftentimes discussed in the use of simple machines. But power, if I look at my equation sheet, like I said, it's just the rate of change of energy, and rates oftentimes are in time. So if I think about my change in energy over my change in time, this is what power is. We can also write this as work over change in time. Whatever work or energy is done over time, this is known as power. So today, we're going to look at 3 different scenarios with a cart and a ramp and compare, contrast, measure the power that is exerted on this object in these different scenarios, okay? I'm going to spin you around, and we can check out the ramp. Before I spin you around, I'm wearing my Christmas holiday FMP sweatshirt, and while I'm doing it, making this video, come check this out. Are you seeing this crazy snow out here? It's snowing like crazy. It was raining this morning. Now it's snowing. I think the sweater weather is here to stay. You know what I'm saying? All right, here's the lab. I've got 3 scenarios. The first scenario is a car being lifted to a certain height. So I've got this cart right here, and it's a blue cart, and I can measure, I can change its potential energy from the ground up to the height of the ramp. Get this chair out of the way. So this would be, lifting it straight vertically. The other scenario is going to be pulling it up the ramp with a parallel force on a essentially frictionless with these frictionless wheels. If I can get it in the right track, there it is. This would be scenario 2. And scenario 3 is going to be flipping this thing over so the wheels are no longer engaged and pulling it, and you can even hear that non-mechanical friction. These are the 3 scenarios that we have for this lab. Stop rolling. These are the 3 scenarios. So let's go ahead and sketch a picture real quick so that we know what we are doing. All right, I've got this ramp here. Ramp. The cart can be here below the table and lifted up with the force of the lift. And if we make sure that these are moving at a constant velocity, that's equal to Fg. We have the cart being here with the force of the pull without friction and with friction, okay? And we're going to call this point over here, we'll call this point A. We'll call it up here point B. We'll call it at the bottom, we'll call it point C. And over here, we'll call it point D. And then we'll talk about this surface is either going to have some friction or no friction based on whether or not the cart is flipped over or on its wheels. So if I'm thinking about the measurements I need to take in order to find the power in the 3 scenarios, I'm definitely going to need whatever the change in energy or work is. And if I think about this, the change in energy or work is going to be equal to whatever force I apply times the distance it's applied over divided by the change in time. So at home, I am going to need you to get your stopwatch out and time this. The YouTube timer is not going to be accurate enough for us. I'm going to need you to get out a timer to time this motion as I move it. Now, I promise here in the classroom, I will move it at a constant force and report that force to you. I will also report the distances to you. So I'll take care of the numerator, you take care of the denominator. So I'm going to give you a second. I'm going to grab my meter stick. You go ahead and grab your stopwatch so we can gather some data together. All right, here we go. First things first, let's lift this thing up first. We're going to go from point A to point B, which is the ground, straight up. And that height is exactly, roughly, approximately exactly 37 centimeters. 0.37. 0.37 meters is the height from A up to B. 0.37 meters. That's my height. Time to take some time. Here's how I'm going to do it. I'm going to start with the bottom of the cart at the surface of the table. In order to lift this 37 centimeters, I need to make sure the bottom of the cart is up to the top of the ramp. You're timing it from the time I say go until the time it goes up to the top of the ramp. Okay? I will look at my force while I do this. And as I move it at a constant speed, my force is going to be 2.56. 2.56 newtons is the force being applied. All right, you ready? When I say go, you start. When you see the cart hit the top of the ramp, you stop. You ready? There it is. 3, 2, 1, go. Let's try it again. Let's try it again. Trial 2. Trial 2. 3, 2, 1, go. There it is again. I'm going to try to go to constant speed. 3, 2, 1, go. Okay. 3 trials, average amount. That was scenario 1 from A to B. Let's go from B to C with no friction. B to C with no friction. We are going to travel approximately, no, let's make it exactly. We're going to travel exactly 1 meter. Exactly 1 meter from 20 centimeters up the ramp here to 120 centimeters up here. So when the front of my cart reaches this point up here, you'll stop your timer. Here we go. I have to read the force in action now. So we're going to start in 3, 2, 1, go. That's 1. I got 0.5, by the way, 0.5 newtons. Let's try it again. 3, 2, 1, go. That was more like 0.6 newtons, 0.6 newtons. Let's see what I get this time. 3, 2, 1, go. 0.6. 0.6 newtons is the force we're going to record there. 0.6 newtons. 0.6 newtons over that 1 meter. I'm going to record some data for us. 1 meter from C to D. And when the coefficient of friction is 0, we saw that the force is equal to 0.6 newtons. We'll see what happens when the coefficient is not 0. And we said the force when I lifted it up was 2.6 newtons. All right, last one. Last one, we're flipping this thing over. Now we've got friction. Now there's friction on my surface. Let's go ahead and see what I have here. When there is friction, I've got, that was the first trial. 3, 2, 1, go. Last trial. 3, 2, 1, go. 1 newton. I see 1 newton, and you should have 3 times. So you've got 3 times, 3 different trials for each of the 3 scenarios. Without friction, the force was 0.6. With friction, the force is 1.0 newtons. Lifting it straight up, the force was 2.6 newtons. So now I can go look at a data table, and I can say, okay, let's compare the various forces and the various energies and the various powers based on times that you got at home. What I want you to do is think about a couple of things. Number 1, I want you to think about the FBD we have going straight up. Okay? Is there any work done other than the work of gravity? The answer is no. Okay? No. I'm sorry, the work being pulled up. What else is happening? Are the energies mechanical? Is there work being done based on your system and whatnot? Is all energy being added positive? Is some negative? And so on and so forth. I want you to think also about the 2 differences between the C and D trip. So the C and D trip, I see a couple different things, right? C and D trip 1, right? So if I talk about the first one up the ramp, here's the ramp, here's my mass. I obviously pulled it up the ramp with the force of pull. There's, of course, a normal force. And obviously there's gravity here. But there was no friction initially. There was no friction. So the only forces that I'm adding to my system that I'm pulling up, the only force being added is the force of pull as I pull it up the ramp. Obviously there's UG being added to the system and whatnot. But as I start from rest and I end at rest, I start and end at rest, the only change in energy is UG, and that change in UG is coming from the energy of the pull. But in the second scenario, here's my box, there's FG, there is still in fact a normal force. Of course I'm pulling it, and I'm pulling it harder, but in this time there is an amount of force of friction. I wonder how I can find that force of friction. I wonder how I might compare those two scenarios to find the amount of friction that was there, that wasn't there to begin with, but was there when I turned it over. How can I find the difference in the force of friction? Remember, they were both going at a constant speed, so that's curious. Now, there are questions in your packet that I'm going to ask you to answer, and I want you to go ahead and try those. So if you weren't in class today, you've got some data, you've got a clearer picture. If your data in class wasn't great and you were like, oh no, I forgot to write it all down, now you have that data. We got to see the snow, which is exciting. And yeah, if you got any questions, as always, put in the comments. Ask me in class, send me an email. But until next time, see ya!